We have identified which effects matter. Now comes the work of turning that identification into something you can actually use. A tested model, a prediction equation, and a clean bill of health from the residuals. That is the arc of this lecture. Let me orient you to where we stand and where we are headed. In the previous session, a half-normal plot gave us a graphical answer to the question of which effects are real. For our chemical yield experiment, the answer was 3. The main effect of temperature, the main effect of temperature, the main effect of reaction time, and their interaction. The remaining 12 effects were judged to be noise. That graphical step is finished. What remains is a 4-part workflow. First, we pool those 12 negligible effects into an error estimate. Second, we use that error to run significance tests, not to discover anything new, but to check internal consistency. Third, we write a prediction equation that lets us estimate yield anywhere inside the experimental region, not just at the 16 corners we actually ran. And fourth, we examine the residuals to make sure the model is adequate. Each step feeds the next, and together they constitute the standard deliverable for an unreplicated factorial analysis. Before we dive into the mechanics, let me make sure the experimental context is sharp in your mind, because every number we compute today lives inside this study. We ran 16 experiments, a full 2 to the 4 factorial, varying temperature, catalyst loading, reaction time, and solvent ratio. The response is % yield of a chemical synthesis reaction. No run was replicated, which means the data contain no pure error. That is the central challenge. The model we are building has the form predicted yield equals an intercept plus a coefficient on temperature plus a coefficient on reaction time plus a coefficient on their interaction. The half-normal plot told us those 3 terms belong. Everything else, 12 effects, is our raw material for constructing an error term. Here is the full data set. 16 rows, 1 per experimental run in standard order. Each factor is coded, -1 for the low level, +1 for the high level. Look at the yield column and let the range sink in. The lowest yield in the table is 62.6%, run 3, where temperature is low, catalyst loading is high, reaction time is low, and solvent ratio is low. The highest yields cluster around 90%, run 6, 8, 14, and 16. And if you look at what those runs have in common, temperature is at its high level and reaction time is at its high level, and reaction time is at its high level. That pattern is exactly what the half-normal plot captured. Now notice what is absent. There is no repeated run, no duplicate row. Without replication, there is no row-by-row estimate of pure experimental error. That is why we need the pooling strategy we are about to build. So how do we get an error estimate when there is no replication? The answer rests on a judgment we already made. When the half-normal plot identified 12 effects as negligible, we were saying these effects are indistinguishable from noise. If that judgment is correct, then the variation those 12 effects explain is in fact noise, and we can pool their sums of squares to form a mean squared error. The mechanics are straightforward. Each negligible effect contributes 1 sum of squares and 1 degree of freedom. Pool all 12, divide the total sum of squares by 12, and you have a mean squared error with 12 degrees of freedom. That is a solid error estimate. 12 degrees of freedom is enough to give the f-tests real power. The formula is simply mean squared error equals the sum of the negligible sums of squares divided by the number of negligible effects. The critical word in all of this is honest. Pooling is only valid when the graphical selection was done carefully and without cherry picking. If you were tempted to call an effect negligible because it was convenient, the error estimate you build will be corrupted. This brings us to the most important judgment call in the entire workflow. What happens if you pool an effect that is actually real? Think about what the expected value of the mean squared error becomes in that case. It is no longer just sigma squared, the true variance. It picks up a positive contribution from the squared coefficient of the wrongly pooled effect. The error estimate is inflated, and an inflated error estimate makes the F-ratios for the effects you kept smaller than they should be. You lose power. In the worst case, a truly active effect fails to look significant, and you walk away thinking the factor does not matter when it does. The practical rule is conservative. When you are genuinely uncertain about an effect, when it sits in the ambiguous middle of the half-normal plot, keep it in the model. A slightly larger model with one extra term costs you 1 degree of freedom. A corrupted error term costs you the validity of every test you run. The asymmetry is clear. Err on the side of inclusion. Let me now set up the pooling calculation explicitly so you can see exactly what we are doing. We fit 2 models. The first is the full model with all 15 effects. The second is the reduced model retaining only temperature, reaction time, and their interaction. The residual sum of squares from the reduced model is the sum of the sums of squares for all 12 dropped effects. That equality is exact, not approximate, because in a balanced 2 to the k design, the effects are orthogonal. So the residual sum of squares from the reduced model is our pooled error sum of squares, and dividing by 12 gives us the mean squared error. That is the number we will use as the denominator in every f-test. Here is the ANOVA table from the reduced model. Focus first on the bottom row, the residuals row. It shows 12 degrees of freedom. Exactly as expected, 1 for each of the 12 effects the half-normal plot judged negligible. The residual sum of squares is 35.3, and dividing by 12 gives a mean squared error of 2.94. Now look at the 3 active effects. Temperature has a sum of squares of 939. Reaction time has 438. The interaction has 294. Compare those to the residual mean square of 2.94. The active effects are not just larger. They are 100 to 300 times larger. That ratio is a sanity check. If the active effects were only 2 or 3 times the noise, you would want to go back and reconsider the graphical selection. Here, the separation is dramatic, which gives us confidence that the pooling made sense. This mean squared error of 2.94 is now our working estimate of experimental noise. It will be the denominator in the f-tests and the basis for confidence intervals on predictions. Before we read the f-test results, I want to make sure you understand what those tests actually are and what they are not. In a standard regression or ANOVA, the error term is estimated from data that are independent of the model selection process. Here, that is not the case. The error term was built from effects that the same analyst, looking at the same data, judged to be negligible. The f-tests are therefore circular in a precise sense. The denominator was constructed by setting aside effects that looked small, and the numerator contains effects that looked large. What the f-test can tell you is whether the active effects are consistent with the noise pool. A large f-ratio says, yes, the effects we kept are many times larger than the effects we discarded, which is internally coherent. A small f-ratio, one that fails to reach significance, would be a warning sign. It would mean the active effects are not clearly larger than the noise pool, which suggests either the graphical selection was wrong or the error estimate is inflated. In that case, the right response is to revisit the selection, not to conclude the effects are zero. Let me sharpen this point, because it is easy to misread f-tests. In this context, a significant p-value here does not provide fresh, independent evidence that the effect is real. The graphical selection already made that call. What the F-test does is check whether the call's internally consistent. Think of it as a self-audit. If the audit passes large F, small p, you have confirmation that the active effects genuinely dominate the noise pool. If the audit fails, you have a signal that something in the analysis needs revisiting. The practical implication: report the F-tests, interpret them as consistency checks, and be explicit with your audience that the error term was constructed from the same data used for selection. This is standard practice in unreplicated factorial analysis, and any experienced practitioner will understand the construction, but it is worth stating clearly. Now let us set up the F-radio calculations explicitly. For each of the three retained terms, the F-radio is simply the mean square for that effect divided by the pooled mean squared error of 2.94. So F for temperature is the mean square for temperature divided by 2.94. F for reaction time is its mean square divided by 2.94. And F for the interaction is its mean square divided by 2.94. Each of these has 1 degree of freedom in the numerator and 12 in the denominator. Here are the F-test results. Temperature F equals 319, p-value rounds to 0. Reaction time, F equals 149, p-value rounds to 0. The interaction, F equals 99.8, p-value rounds to 0. Every one of these is enormous. The smallest, the interaction at 99.8, still means the interaction mean square is 100 times the noise. These are not borderline cases. The active effects are so far above the noise floor that the consistency check passes with no ambiguity. What does this mean in practice? It means the graphical selection was sound. The 3 effects we retained are genuinely dominant relative to the 12 we discarded. We can proceed with confidence to write the prediction equation and examine the residuals. If any of these F-radios had been, say, 3 or 4 close to the critical value, we would need to pause and reconsider. Here, there is no such concern. With the model validated, we can now write the prediction equation. The goal is a formula that takes coded factor settings as inputs and returns a predicted yield. This is more useful than a table of corner point estimates because it lets you predict at any point inside the experimental region, not just the 16 corners you ran. The equation has the form predicted yield equals B0 plus BA times XA plus BC times XC plus BAC times XC times XA times XC. The coefficients are estimated by fitting the reduced model to the 16 observations. In a balanced 2 to the k design, each coefficient is exactly half the corresponding factorial effect estimate. That relationship is worth knowing because it connects the regression coefficients back to the effect estimates you computed from the half-normal plot. The coded units are essential here. Because every factor runs from -1 to +1, the coefficients are directly comparable in magnitude. A larger absolute coefficient means a larger contribution to yield, and you can compare temperature's coefficient to reaction time's coefficient without worrying about different physical scales. The interaction term deserves special attention because it changes how you read the main effects. The partial derivative of predicted yield with respect to XA, the slope of yield on temperature, is BA plus BAC times XC. That slope is not a constant. It depends on where reaction time is set. At XC equals +1 reaction time at its high level, the temperature slope is BA plus BAC. At XC equals -1 reaction time at its low level, the temperature slope is BA minus BAC. If BAC is large, those two slopes can be very different. That is the essence of an interaction. The effect of one factor depends on the level of another. You cannot read temperature's main effect in isolation and expect it to hold across all levels of reaction time. The interaction coefficient quantifies exactly how much the slope changes. Let me set up the prediction calculation. We extract the four fitted coefficients from the reduced model: the intercept, the temperature coefficient, the reaction time coefficient, and the interaction coefficient, and write the explicit equation with rounded values. Then we evaluated at 4 points: the center of the design space, the high corner, the high-low corner, and an interior point that sits between the corners. The center and the interior point are the ones that demonstrate the real practical value of the equation. Here are the predictions at 4 points in coded space. At the center, temperature equals 0, reaction time equals 0. The predicted yield is 72.9%. That is the grand mean of the fitted model, and it is a useful anchor. Now compare the two high temperature points. When both temperature and reaction time are at their high levels, the predicted yield is 90.1%. When temperature is high but reaction time is low, the predicted yield drops to 71.0%. The difference is 19.1 percentage points. That gap is twice the interaction coefficient, and it is the interaction made tangible. Running temperature high is only beneficial when reaction time is also high. If you ran temperature high with reaction time low, you would get almost the same yield as the center point. The fourth row, temperature at 0.5, reaction time at negative 0.3, gives a predicted yield of 74.5%. That point was never run in the experiment. The equation is interpolating inside the design space, which is exactly what it is designed to do. This is the practical payoff. You can now answer questions about conditions you did not physically test, as long as you stay within the range of the factors you varied. We have a fitted model and a prediction equation. The next question is, does the model actually fit the data well? Are there patterns in the data that the model has missed? Residual analysis is how we answer that. A residual is simply the difference between what was observed and what the model predicted. EI equals YI minus Y hat I. If the model is correct, the residuals should look like random draws from a normal distribution with mean 0 and constant variance. Any departure from that picture is a signal that something is wrong. We use 4 diagnostic plots, each designed to catch a different failure mode. Residuals plotted against run order reveal drift or time-related effects. If there is a trend, some lurking variable changed over the course of the experiment. Residuals plotted against fitted values reveal non-constant variance or missing curvature. A funnel shape means the variance grows with the mean, and a curve means the model needs a quadratic term. Residuals plotted against individual factors reveal whether those factors have residual structure the model did not capture. Let me be precise about what each plot should look like when the model is adequate. In every case, the answer is the same: random scatter around 0 with no discernible pattern. A funnel shape in the fitted value plot, where the spread of residuals increases as the fitted value increases, is the signature of heteroscedasticity. The variance is not constant, and the standard errors on your coefficients are wrong. A curve in the fitted value plot, where residuals are systematically positive in the middle and negative at the ends, or vice versa, means the true relationship has curvature that a linear model cannot capture. A trend in the run order plot, residuals drifting upward or downward over time, means something changed during the experiment that is not in the model. And on the normal probability plot, an S-curve means the error distribution is skewed, while heavy tails bending away from the line mean the distribution has more extreme values than a normal would produce. None of these patterns is fatal by itself, but each one tells you something specific about what the model is missing, and each one points toward a specific remedy. Let me set up the residual calculations. We take the fitted values from the reduced model, the model with temperature, reaction time, and their interaction, and subtract them from the observed yields. That gives us 16 residuals, 1 per run. We then plot those residuals against four things: run order, fitted values, coded temperature, and coded reaction time. Four panels, each asking a different diagnostic question. The four diagnostic panels for the yield experiment all show the same reassuring picture: random scatter around zero with no systematic pattern. In the run order panel, the residuals bounce around zero without any upward or downward drift. That tells us there was no time-related lurking variable, no gradual change in ambient conditions, reagent quality, or operator technique over the course of the 16 runs. In the fitted values panel, the spread of residuals is roughly constant across the range of predicted yields. There is no funnel shape, so the variance is not growing with the mean. There is no curve, so the linear plus interaction model is capturing the shape of the relationship adequately. The factor panels, residuals against temperature and against reaction time, show no residual structure. The model has extracted what those factors contribute. There is nothing left in the residuals that is systematically related to either factor. All four panels look like noise. That is exactly what we want, and it gives us confidence that the reduced model is adequate for this data. One more diagnostic to run, the normal probability plot of the residuals. The question it answers is whether the Gaussian error assumption is defensible. The construction is straightforward. Sort the residuals from smallest to largest and plot each one against the theoretical quantile it would have if it came from a standard normal distribution. If the errors are truly normal, the point should fall near a straight diagonal line. The normal probability plot for the yield experiment shows the 16 residuals falling close to the diagonal reference line. There is no pronounced S-curve, which would indicate skewness, and the tails do not bend sharply away from the line, which would indicate a heavy tail distribution or outliers. A few points at the extremes stray slightly from the line, but that is entirely expected with only 16 observations. Random sampling variation alone will produce some deviation from a perfect line at this sample size. The question is not whether the points are perfectly on the line. They never are, but whether there is a systematic departure that suggests the normal assumption is wrong. Here, there is none. The Gaussian assumption is defensible. Combined with the four clean diagnostic panels, this means the reduced model passes all the standard adequacy checks. We have a model we can trust. Let me pull together what the yield experiment taught us. 3 effects drive yield, temperature, reaction time, and their interaction. The interaction is the most important finding because it means you cannot optimize temperature without knowing where reaction time is set. Pooling the 12 negligible effects gave us a 12-degree of freedom error estimate, solid enough to support meaningful tests. The F-test confirmed internal consistency. The active effects are 100 to 300 times the noise, which is a dramatic and reassuring separation. The prediction equation works at any interior point in coded space, not just the corners we ran. That is its practical value. It lets you answer questions about conditions you did not physically test. The residual plots confirmed model adequacy, no patterns, no trends, no violations of the constant variance or normality assumptions. This 5-step workflow, graphical selection, pooling, F-testing, prediction equation, residual diagnostics, is the standard deliverable for unreplicated 2-to-the-k analyses. It is what a practitioner hands to a client or a decision maker. Now let us practice it on a second experiment. The practice experiment is a paper helicopter study. 8 runs, a full 2^3 factorial, 3 factors, wing length, body width, and paper weight. The response is flight time in seconds. A half-normal plot from a prior analysis identified wing length and the wing length by body width interaction as active. The remaining 5 effects, body width alone, paper weight alone, and the 3-way and 2-way interactions involving paper weight, are judged negligible. The task is identical to what we just did for the yield experiment. Pool the 5 negligible effects into an error estimate, run f-tests as a consistency check, write the prediction equation, and examine the residuals. The workflow does not change with the experiment. Only the numbers do. Here is the helicopter dataset. 8 rows, 1 per run, in standard order. Wing length, body width, and paper weight are each coded -1 and +1. The response is flight time in seconds. Look at the flight times and see if you can spot the pattern before we compute anything. Runs with wing length at +1, runs 2, 4, 6, and 8 tend to have longer flight times. And within those, the longest times occur when body width is also at +1, runs 4 and 8, with flight times of 5.66 and 5.66 and 5.67 seconds. That is the wing-by-body interaction showing up in the raw data. Runs with wing length at -1 and body width at +1, runs 3 and 7 have the shortest times, 0.93 and 0.60 seconds. The interaction is strong and visible even before any analysis. 5 effects will be pooled to form the error. With only 8 runs and 3 active parameters plus an intercept, we have 5 degrees of freedom for error, fewer than the 12 we had for the yield experiment, but still workable. Let me set up the helicopter analysis. We fit the reduced model retaining only wing length and the wing-by-body interaction. The residual sum of squares from that model equals the combined sum of squares of the 5 dropped effects by orthogonality. Dividing by 5 gives the mean squared error. We then compute f radios for wing length and the interaction, extract the fitted coefficients to write the prediction equation, and prepare the residuals for diagnostic plotting. Here is the ANOVA table for the helicopter experiment. The residuals row shows 5 degrees of freedom and a mean squared error of 0.017. That is a very small noise estimate. The helicopter flight times are quite consistent once you account for wing length and the interaction. Now look at the active effects. Wing length has a mean square of 18.2. The interaction has a mean square of 7.09. Compare those to the residual mean square of 0.017. Wing length is over 1,000 times the noise. The interaction is over 400 times the noise. These F radios, 1084 for wing length and 422 for the interaction, are extraordinary. The separation between signal and noise is even more dramatic here than in the yield experiment. The consistency check passes emphatically. The graphical selection was sound, and we can proceed with full confidence to the prediction equation and residual diagnostics. Here are the predictions at 4 points in coded space for the helicopter model. At the center, wing length 0, body width 0, the predicted flight time is 3.23 seconds. That is the grand mean of the fitted model. Now compare the 2 high wing length points. When both wing length and body width are at their high levels, the predicted flight time is 5.68 seconds. When wing length is high but body width is low, the predicted time drops to 3.79 seconds. The difference is 1.89 seconds, nearly 2 full seconds of flight time, attributable entirely to the interaction. Body width on its own has no main effect in this model, but it dramatically modifies the effect of wing length. A long wing with a wide body flies much longer than a long wing with a narrow body. The interior point. Wing length at 0.5, body width at 0.5, gives a predicted flight time of 4.22 seconds. That point was never physically tested. The equation is interpolating, and that is exactly what makes it useful for optimization. You can search the interior of the design space without running additional experiments. Let me set up the residual diagnostics for the helicopter model. We compute the 8 residuals, observed minus fitted, and plot them against run order, fitted values, wing length, and body width. Then we add a normal probability plot. With only 8 runs, the plots will be sparse, but we are looking for gross patterns, not fine detail. The 4 diagnostic panels for the helicopter experiment show no systematic patterns. The run order panel shows residuals bouncing around 0 with no trend, no time-related lurking variable. The fitted values panel shows roughly constant spread, no funnel, no curve. The factor panels show no residual structure against wing length or body width. Now, with 8 runs, these plots are sparse. You are looking at 8 points per panel, and random variation alone can create apparent patterns in small samples. The discipline here is to ask, is there a clear, systematic pattern, a monotone trend, a pronounced curve, a dramatic change in spread, or is it just the noise you would expect from 8 observations? In these panels, there is no clear systematic pattern. The model appears adequate. If any panel had shown something concerning, say, residuals that increase steadily with run number, suggesting a time trend, the right response would be to investigate before trusting the prediction equation. Here, no such investigation is needed. The normal probability plot for the helicopter residuals shows 8 points following the diagonal reference line without a pronounced S-curve or heavy tail departure. 8 points make a very sparse normal plot. You simply cannot detect subtle departures from normality with this few observations. What you can detect is a gross departure, a point sitting far from the line, or a clear S-shape across all 8 points. Neither is present here. The points are consistent with the Gaussian assumption, and that is all we can responsibly conclude from 8 observations. The helicopter model passes its diagnostic checks. The prediction equation is trustworthy within the experimental region, and the Gaussian error assumption is defensible. Let me close with the key lessons from the helicopter practice, because they generalize beyond this specific experiment. First, the F-tests are circular. The error term was built from effects already set aside by graphical selection. The tests check internal consistency, not independent evidence. Always report them with that caveat. Second, residual plots reveal what the model missed, not what it captured. A clean set of plots means the model is adequate. A pattern in the plots is a signal pointing towards something the model needs. Third, with fewer runs, the diagnostic plots are sparser. With 8 runs, you look for gross patterns, clear trends, dramatic changes in spread, points far from the normal line. You cannot detect subtle departures, and you should not pretend you can. And fourth, the workflow is identical regardless of experiment size. 2 to the 3 or 2 to the 4, 8 runs or 16, you pool, you test, you predict, you diagnose. The steps do not change, the numbers do.